Today we're going to talk about imaginary numbers and complex roots. First, let's talk about the number systems you're familiar with. If you go way back in the history of humankind, there was no real need for numbers in the early days. You didn't own enough to have to count anything. Then people started to have more than one of something. So imagine you have a herd of sheep and you're taking them out into the pasture and you want to make sure they all come back. So what people used to do is they used to tie knots in pieces of string, and each knot would represent one sheep. And as they came back, you'd keep track of how many were there. Another system, you'd pick up a rock for every time a sheep left, and then when they came back, you'd take the rocks out of your hand and put them down. If there were any left in your hand, you knew that's how many sheep you have to go looking for. Now that's all well and good until you trip with a pile of rocks in your hand, and all of a sudden you have no idea how many sheep are out there and how many you've just lost on the ground. So numbers, we started counting things. So the numbers 1, 2, 3, 4, until the highest number you can imagine, these are known as the natural numbers. They occur quite naturally. Young children understand exactly what these numbers are. So let's think, what numbers do we need after that and why? As our civilizations became a little more complicated, we started to need negative numbers. They would come in with trade. So negative numbers come in quite logically, but there's one more number that comes in before the negatives, and that number is 0. When we add 0 to the natural numbers, it's called the whole number system. And it's interesting, 0 didn't really arrive before the negatives, and there were wars fought over 0. People were very upset with the concept of 0. If you want to think about why, if I ask you to hold up 5 fingers, okay, you can do that. If I ask you to hold up 0 fingers, those aren't 0 fingers, that's a fist that you're waving at me. And 0 fingers looks a whole lot like 0 apples and 0 watermelons. So the idea of 0 took people a long time to understand. Now, it would be also good if we could have a visual of what we're talking about here. So the natural numbers, the numbers 1, 2, 3, 4, 5, 6, 7, all the way on to the biggest number you can think of, those are the natural numbers. Then we add to that the number 0, but include the naturals. So the whole numbers are not much bigger than the naturals. They include all the natural numbers, and we just add in 0, so they're a little bit bigger than the natural numbers, and these are the whole numbers. Then we're going to start trading, and we're going to need some negatives, because you're going to owe me something when I sell you something. So when we get the negative integers in there, that's going to take us to the negatives and 0 and the naturals are called the integers. So 1, 2, 3, 4, 5, 6, 7, 0, and all the negatives, that gives us the integers. Now you were pretty happy with these abbreviations, N for natural, W for whole, Z for integer. And that comes from the German, where this just means numbers. And we did really well with these numbers for quite some time. Now think about what other numbers you might want. Something that's not an integer. Hopefully, you're thinking about decimals. And in particular, the decimals we're going to talk about are the ones that could be fractions. So 1/3 of a piece of cloth, half of a cow. So anything that can be written as a fraction, so A and B are both integers, and make sure B is not 0, otherwise we're in trouble. These are known as repeating terminating decimals. The fraction 1/2, 0.5, terminates. The fraction 1/3, 0.333333 repeats. So where are the rationals compared to the naturals, the wholes, and the integers? Can you write the number 4 as a fraction? I think you can, 4 over 1. So the rational numbers include all of these numbers again, and then they're just a whole lot bigger. So these are your rational numbers. Now, why Q? Why are we using the letter Q for rational? I see a fraction. otherwise known as a quotient. Maybe there's a good reason for it. Okay, what numbers are next? We've dealt with decimals, repeating, terminating decimals. There are also non-repeating, non-terminating decimals. An example of that, pi, 3.14159, etc., goes on forever and it does not terminate. Root 2, 1.414, etc., might look like it repeats, but take it further and you'll find it doesn't. So the irrational numbers. Now, the abbreviation for this is not Q. So this symbol just means not Q. If you're non-repeating, non-terminating, you are not a member of these decimals. So either you are rational or irrational. So the irrational numbers don't have anything in common with any of these numbers we've looked at so far. You are either rational or you're irrational. Now, when you combine all of these numbers together, that is known as the real number system, the rationals combined with the irrationals. And up until now, you've been pretty content working with this number system. You've worked in the reals, which is essentially every number you can think of. So what's next? Is there really any need for another number? There is, but we're going to talk about where it came from first. So it was in 1545, there's an Italian who was looking for a solution to the general cubic. Now, you're familiar with the equation to solve the general quadratic. Negative b plus or minus the square root of b squared minus 4ac. That's a good use of an irrational number. So we had good reason for irrational numbers when we had this formula. When Cardano was working with his solution, he had a square root inside a square root. And when he tested his formula, he worked with an equation that he knew the answer to. And he got stuck because inside this square root, he had a negative number. And he said, I know there is an answer. I know there's a solution to this. My formula should work. He said, if only I would be allowed to take the square root of a negative number, I could do this. So he did. He worked with the square root of -1, and he's going to use I to represent it. Now, years later, it was Descartes who said, let's call this an imaginary number. So we have the complex number system. The complex number system takes every number that you're familiar with and allows you to add in an imaginary number. So an example, 5 is a number that you're very familiar with. B can be any member of the reals. How about root 3? If I put I on that, that's an example of a complex number. You don't really know what to do with that yet, but that's a complex number. So question for you. Where are the complex numbers in relation to the reals? Is 7 a complex number, meaning are the reals inside the complex number system? Let's look at our definition. A is a real number. Check. BI. Okay, so let's add BI, but we want the answer to be 7. So what if we do that? So 7 is a complex number. So that means the complex numbers are every number that you've ever known existed. And then you can add any value of I to that. So the complex number system is gigantic. It includes everything you know, plus all these new numbers. How do we use them? So again, here's Cardano. There was his formula. He needed a negative underneath. So he said, I'm going to create a number. I'm going to call it I. Now, it's a little unfortunate that it's called imaginary, because you're going to look at that and say, they don't exist. People really didn't like negatives, and they didn't really like 0 either. So I want you to think of an imaginary number more as a concept. What I mean by that, you can show me 4 apples. You cannot show me -4 apples. The idea of -4 apples is an important one. It means you owe me 4 apples, but you can't really show it to me. So you're not going to be able to show me an imaginary number either. but they're useful. How and where are they useful? I actually took a course in university that was all about solving calculus problems using imaginary numbers. Why would you do it? There were formulas that were so complicated that we just could not solve these in the real number system. We changed our numbers to complex. There were different formulas that worked with those, got an answer, and then we're able to express the answer back in the reals. So these are useful. Computer scientists, you might have recognized the first picture on the screen as the Mandelbrot set, and that comes from working with imaginary numbers as well. So anyone who goes really far in engineering or math, you will see these again, and you'll also see them with some simple ideas today. So we're going to write the root of minus 25 as root 25 times root minus 1. Multiply those together, there's your negative 25. Now, what did we say the root of negative 1 was going to be equal? We said I is going to equal the root of negative 1. So every time you see root negative 1, you replace it with I. So the square root of negative 25 is 5i. Let's try another one. Square root of negative 64. We can write that as root 64 times negative 1. The root of negative 1 is going to be replaced with I, and we know the square root of 64 is 8. So the root of negative 64 is 8i. Isn't that lovely? All right, what does that have to do with graphing? Let's go back to this question. We're going to sketch this graph. We're going to find x-intercept, y-intercept, and degree, just like we did before. You can ask yourself, what makes that one 0? I think the answer to that is 4. What makes this one 0? If we solve that, we can take the 9 to the other side. And what squares to give you negative 9? Well, it would be plus or minus the square root of negative 9. We can rewrite the square root of negative 9. That would be root 9 and root negative 1. Square root of 9 is 3. Square root of negative 1 is I. Okay, so we actually get 3 values for x that solve this equation. But I only put 1 here. The reason I'm only going to put 1 here is when you draw your graph, we draw the graph in the real number system. This is a real number. This is a real number. So we can find 4 on the x-axis, but we can't find plus or minus 3i if we're dealing with real numbers. So this information does not change what we're doing. Y-intercept, you're going to let x equal 0. What's our y-intercept? Getting negative 36, the degree, 1, 2, 3. And now let's look at the graph. We have degree 3, it's going to start here. It's going to end here. Now, what matters? We know there's a couple of other roots. So we are not just drawing ourselves a straight line. This is not a straight line. It's going to have a bend in it. We're not entirely sure where. So what you're learning today is you're learning to recognize that having complex roots changes the shape of the graph. You can't see them. That's still our real root, but it does have an impact on the graph. So essentially, you just have to expect more of a curved graph going through this one. I would have probably drawn something like that. So we might draw something that's a little bit wrong, but as long as you're not drawing a straight line, you understand that these values have an impact on the graph. Let's try another one. Oops, there's an answer coming out ahead of time. So let's sketch this one. If we let that equal 0, what would let this one equal 0? I think that's 1. This one, negative 1. This one, you can try factoring it, but I don't think it works. And we're going to put it into the quadratic. Putting it into the quadratic, we end up with a negative under the root sign. That's where that I came from. So we have 2 real roots and these 2 imaginary roots. The x-intercept, 1 and negative 1. The y-intercept, if you let all those x's equal 0, what do we end up with? Getting negative 2, and the degree, 1, 2, 3, 4. So we know we're going to have a graph that starts here, ends there, crosses at -1 and 1, y-intercept of -2. So we'll draw something like this. And then we'll check the answer. And we'll see it has this weird kind of bend here that we weren't expecting. Or were we? We knew there were a couple of extra roots and we're going to get a slightly different shape. So again, all we're doing is we're saying when you see complex roots, expect the shape of the graph to be a little bit different than what you would draw based simply on this information. The other thing we can do is talk about the nature of the roots. So we're going to look at some polynomials, and I'm going to tell you they all are degree 5. And here's something interesting. Polynomial of degree n has n roots. So degree 5, we're expecting 5 roots. Now they could be real, or they could be complex. Complex means there's an imaginary number involved. So let's look at this. How do we figure out the roots of this? I would start by circling all the x-intercepts. So crossing through here, that's one intercept. So that's another one intercept. Now this shape is different. That is not one intercept, is it? I'm going to say that that's 3. Now, you might look at that and say, okay, hold on a second. There's an extra bend that could be 3 or 5 or 7 or 9, so we have to count. I've got 1 here and 1 there. I'm allowed 5. It's got to be 3. There's no way that could have been 5 or 7. We know it's more than 1 because it didn't go straight through. A little bit of a bend means there's 3. So if we describe this one, we would call it one real and distinct. The word distinct just means different from all the other roots. This one then, real and distinct. These ones, also real. Real because you see them on the number line, meaning they're real numbers, but they're equal. So if you were asked to describe the roots, you'd say I have 1 real and distinct, 1 real and distinct, 3 real and equal. You try this one. I'm telling you the degree is 5, so we're looking for 5 roots. Circle all the x-intercepts. This one just passed through, so I'm going to say that's 1 intercept. This one passed through, that's 1 intercept. That one passed through, that's 1 intercept. So 1, I can see it, it's a real number, 1 real and distinct. 1, we can see it, different from all the others, 1 real and distinct. 1, I can see it, different from the others, real and distinct. We're supposed to have 5. So what are the other 2? I hope you said 2 imaginaries. So 2 imaginary or 2 complex roots. So if you were describing the nature of those roots, you'd have 1 real and distinct, 1 real and distinct, 1 real and distinct, 2 imaginaries. Okay, let's try this one. Start by finding all the x-intercepts. And again, what I'm doing there is I'm just looking for where the graph touches or crosses the x-axis. How many roots do we have? Passes through, that's 1. Bounces, 2. Could it be 4? Could it be 6? Could it be 8? We have 5 roots. We've got to have room for these guys. So if we said that was 4, we wouldn't have anyone left for here. So there's another 2 there. 1, we can see it. It's real. There's no one else like it. It's distinct. 2, we can see them. They're real. There's a pair of them, so they're called real and equal. 2, we can see it. That makes it real. There's a pair of them, real and equal. So that's the description of the roots of this polynomial. Now, let's do something slightly different. Tell me which are possible for real numbers, and I want you to give an example, and I'd like you to leave your answer in factored form. When I ask you to do this on a test or an inventory, please don't do any extra work. Leave it in factored form. It's easier for you. It's easier for me. What are we talking about? A quartic function, so that's degree 4. Graph passes through the points 1, 0, 4, 0, 5, 0. Oh, it bounces a 5, 0. So if I were you, I would draw a picture. passes through 1, 0. Passes through 4, 0, bounces 5, 0. If 1 is an x-intercept, what does the factor look like? X minus 1. If 4 is an x-intercept, what does the factor look like? X minus 4. If 5 is an x-intercept with 2 of them, what does the factor look like? X minus 5 happening twice. So our equation then looks like this. You could have drawn a graph that crossed at 1, crossed at 4, bounced at 5. You could have had your graph upside down. So we could have had the same answer with a negative in front, but you cannot change these exponents. So if you said, what if I'd made that 3? Not in this situation, because we're only allowed degree 4 at the end. So you got to make sure you match the degree when you're done. Let's try another one. Quartic, degree 4. 3 imaginary roots, crosses at 1, 0. Okay. So we know where the graph starts and ends if it's positive, and we know it passes through 1, 0. So degree 4 starts here, ends here, passes through 1, 0, and now what? We're certainly not allowed to do this. That's just bad. So let me get rid of that. I don't think you can do this. I don't think that's actually possible at all. So an interesting thing to be aware of. I know just by looking at that number that this is impossible. The reason for that is imaginary roots always come in pairs. Think about it. Where are the roots coming from? Negative b, plus, minus, square root, b squared minus 4ac. You only get your imaginary roots when you have a negative under the square root sign. And we have a plus minus sign. So that means your imaginary roots will always come in pairs. So if I ever ask you to do a question with 1 imaginary root, 3 imaginary roots, 5 imaginary roots, you have a very simple answer. We cannot do that. Okay, your job today, you're going to get familiar with imaginary roots. You're going to draw some graphs. You're going to come up with some equations. Exercise 1 to 4. Have fun.